Welcome back to Ontology Talk, where we're continuing our discussion of sets and set theory as some of the foundational elements to ontology. Today I'd like to start with talking about the Cartesian product, and this is a mathematical operation named after René Descartes of the famous quotation, cogito ergo sum, I think, therefore I am. He did a lot of foundational things in mathematics, and especially in set theory. And the idea of the Cartesian product is really quite simple. It's that if we have two sets, the Cartesian product is the collection of each pair of elements with one taken from each set. So formally it's the tuple x comma y, where x is an element of M1 and y is an element of M2. And we can generalize this to tuples of arbitrary size if we have arbitrary numbers of sets. So if we have sets M1 through n, then the Cartesian product is just the collection of all of the tuples of size n, where each element is taken respectively from one of the sets. And we go through all different alternatives. So if we have two sets, 1, 2, 3, and AB, then we just iterate through all possible combinations, and we get 1A, 2A, 3A, 1B, 2B, 3B, and so on. Or not and so on, that's it. But if we can look at some larger sets or some different sets, we can also look at different combinations. So let's take this example, and if we have the sets 1, 2, 3, and AB, and the Cartesian product of set 1 and set 2 as we've just given, well, can you think of what's the Cartesian product of M2 and M1, and also M1 with itself? Take a minute and maybe pause the video and see if you can figure that out. We can also, of course, try this in Python and have the machine figure it out for us. So here's just an example. Some one line of code is really all it takes to do the Cartesian product, and here it is. Let's look at some special cases. So we can also have a Cartesian product of one set, and that's really sort of the degenerate case. It's just the collection of all one tuples. So essentially we're taking the set and converting all of its elements to tuples and then saying it's the set of all those things. So not terribly interesting. Then there's also the product of the empty set, the Cartesian product of the empty set, and it just has one element, the empty tuple. So it's always important in mathematics to have these general cases. It makes the math work out correctly, even though it might on the surface not look like it's terribly useful. Let's also look at not only the Cartesian product, but the notion of the power set. So we use the notation 2 to the m, where m is a particular set that we're taking the power set of. And so m, the set m, is an element of its power set, and so is the empty set, because of course remember the empty set is a member, or is a subset of all sets. In this case, because we're looking at all of the subsets of the power set, then the empty set becomes a member of the power set. So here's just an example. If we have the set 1, 2, 3, the power set is all of the subsets of 1, 2, 3. The first subset is the empty set. We can take then all the individual elements, those are subsets. So are all the subsets consisting of the pairs of elements, and finally the set itself is in the power set. So take a moment. Can you come up with the power set of the set AB? Here's another example. Let's look at two sets, the numbers 1 through 7, and then the even numbers 2 through 10. Can you compute the Cartesian product of M1 with itself, of M1 and M2, and of M2 and M1, also the power set of M2? And let's keep going a little bit to look at a basic property, the cardinality of the power set. So if we have a set M3 that's just the empty set, what's the size of the power set of the empty set? Then can you figure out what is the power set of a set that just has one element? Now, once you've done those two, can you think of what is the general equation for the size of the power set of any n elements? All right, any set with a cardinality of n, what's the size of the power set? And the answer is it's 2 to the size of the set. So the size of the empty set is 2 to the 0, the power set of the empty set, 2 to the 0, therefore 1, because the empty set is a member of itself. Our empty set is a subset of itself, therefore the empty set is a member of the power set of the empty set. And if we have the set of one element, it's 2 to the 1 in size, the size of the power set, because it contains the empty set and it contains the original set. So it's the empty set and A, and so on. So then can you answer, why wouldn't you calculate the power set of the union of M1 and M2? Well, you wouldn't do that because, at least by hand, because it's going to be a very large number. You've got 7 plus 5 is 13, so it's going to be 2 to the 13th, and you probably don't want to write all that out. So let's look at some of the solutions. Hopefully you've worked these out on paper, or at least convinced yourself that you could work them out on paper, because they're a little bit tedious. So the Cartesian product of set 1 and set 1 is just going to be essentially a square matrix. It's the numbers 1 through 7 coupled with the numbers 1 through 7. If you look at the Cartesian product of sets 1 and 2, it's the numbers from 1 to 7 and the numbers from 2 to 10 that are even. Again, it's all possibilities and tuples of length 2. If you do it the other way around, you get the following. All right. So in terms of the answer here, why don't we compute the power set of the union of M1 and M2? The size of M2 is already, a power set of M2 is already quite large, so your resulting union is also going to be quite very, very large. All right, let's take another look at different kinds of sets. So if we have a set of 3 elements, how about if we look at the Cartesian product of 3 versions of this same set? So it's just going to be as follows, all possibilities. And let's look at how can we code this up in Python. There are many ways to do this. If you search on the internet, you'll see all sorts of versions. The support for sets in Python is a little tricky, especially with regard to the empty set. Sets, of course, are immutable in Python, and their elements also must be immutable. So it makes it a bit of a challenge to do this properly with just sets. So most people implement power sets with lists, which of course takes away a little bit from the nice correspondence we'd like to have of implementing things in sets. But here's one version of such a program, and so try it and see if you can convince yourself why it works and see why it works. So if we run this particular program, we do in fact get the power set if we sort of treat each answer as though it were a set, and we're going to treat the empty set being just a blank line. Let's also talk about set algebras. This is something I just want to mention. I don't really want to go into it. There are people that work deeply in this area. It's an interesting area of mathematics. It's not certainly one that I've studied or that I use, but you should at least be aware of it. So the field of algebra deals with the properties of arithmetic, and we talk about algebraic structures being a particular set, a set of elements that we can work with, and then a set of operators on this set. And there are classes of algebras that have particular properties. There are things called groups and rings and term algebras, and if you hear these terms, then you might know that at least that it comes back to something having to do with set theory. But we're not going to go into this further here, just to make you aware of some of the terminology. Right? And the algebra of sets, we've already started to build it up. We have union, intersection, complement, and so forth, all the things that we looked at with Venn diagrams. There are some algebraic rules that apply. So if we have three sets that are arbitrary subset of some common carrier set, and this could be the natural numbers, it could be letters in the alphabet, or just about anything else, no matter what the particulars of that carrier set are, set theory is still going to follow these rules. Commutativity, neutral elements, absorption, and associativity. And so let's just go through these. So the first one, commutativity, just says for the operators of intersection and union, you can present the arguments in any order. So the union of set 1 and set 2 is the same as the union of set 2 and set 1, the same for intersection. The union of any set with the empty set is the original set, and the intersection of any set with the carrier set is also the original set, because of course the all sets here we've defined as being subsets of a common carrier set. And then associativity, we can perform the same operations in any order. So if we have three sets, M1, M2, M3, and we have the union of 1 with, in parentheses, the union of 2 and 3, it's the same as the union of 1 and 2, and then the union with 3. And the same holds true for intersection. So try testing these in Python. We've already been over these functions of union and intersection. We know that set with just some empty parentheses creates the empty set. So try these out. See if you can run these exercises and see what you get. Okay, so set up these sets M1 and M2 and M3 and try all these different possibilities. There are more algebraic rules. So again, let's say that we have three sets that are arbitrary subsets of some large common carrier set. We've looked at associativity, but then there's also distributivity. If we're mixing union and intersection, then we have to distribute one over the other. So let's look at this first one. So we have the union of one set and the intersection of sets 2 and 3. And so what we do is we then create the intersection of the union of 1 and 2 and the union of 1 and 3. You can think of it as a sort of a multiplication or an operation where we have to take the outside thing and operate over each of the things on the inside. And we sort of flop the position of the operators. So if you can remember this pattern, distributivity will also come up as we look at propositional logic and first order logic. It's a really interesting thing how this structure of operations applies across these different mathematical systems. So this one's important. Complementary elements, so the union and the union of a set and its complement is just the entire carrier set. The intersection of a set and its complement is, by definition, the empty set. If we take the union of a set with itself, it's the original thing. And if we take the intersection of a set with itself, it's the original set. We also have De Morgan's laws. This is something that crops up further as we get into logic as opposed to set theory. If we take the complement of the union of two sets, it's the same as the intersection of the complement of those two sets. This also works for intersection. So you can think of it as we push in the negation to its components, it flips the operator. We'll see this in logic with and or. We'll also see it with flipping quantifiers. Again, a pattern that holds for other mathematics, and we'll need it in the future. And double complement, as we might expect from double negation in natural language. If we negate something twice, or if we take the complement of something twice, we come back to the original thing. All right, so that's it. Just really a review of some basic operations that hopefully many of you have seen if you already have a STEM education, but just this refresher I hope was helpful. Thanks for listening.